In the last lecture of the course, we will learn how to compute the sample size for pilot studies. So a pilot study can be done for two reasons. One is for experimental reasons, to check that you have clear instructions, that you know how to perform the experiment, that if there is some special procedure, you know how to, or people are trained on how to do it, or for statistical reasons. The problem with the statistical reasons is that the amount of information that you collect is very low, as we will see. So typically you get more information from a previous publication than from the pilot study. So a pilot study, from a statistical point of view, could be done when you are, for instance, constructing a lift for aliens and you have never seen an alien. So the first thing you will have to do is to go out, fetch a few aliens, see how large they are, how variable they are, and then you will be able to construct a lift for them. But otherwise, there is no way that you can design your experiment if you don't know, especially the variability of the observations. So the analogy with aliens is that mice are not aliens. So typically they have been studied in many other publications or studies, and the control groups are very well characterized. The treatment groups are not so well characterized. Typically what you are doing is new, but in terms of variability and kind of response, probably they are not extremely far from the response of the normal control counterparts. Okay, so let's see the calculation of this sample size in a number of situations. We will study variance, mean, coefficient of variation, that is a mixture of the two, proportions, and very small proportions. Okay, so let's start with variance. So let's say that you are the first person studying the gene expression of a given gene ever in the world and history, and you want to determine the variance, the standard deviation of this gene expression with a 10% of accuracy and a confidence level of 95%. So this should be standard deviation. So for constructing confidence intervals, you need to know how a particular statistic is distributed. So what you know is that the ratio between the sample variance and the true variance, the population variance, and multiplied by n-1 is distributed as a chi-square distribution with n-1 degrees of freedom. So now you can construct your confidence interval. Your confidence interval uses your statistic, and then it finds two bounds such that from that bound to the left you have alpha half, and from that bound, from the upper bound to the right, you have also alpha half. And then you can compute the it was variance actually, not the standard deviation. Okay, so now you can construct the confidence interval for the variance ratio. So the variance ratio, you want this upper side, which is the most restrictive, the one that is closer to here, you want it to be 1 plus delta. So you want to have a precision of delta, so this has to be 1 plus delta. Okay, so we plug in our data. So we wanted an accuracy of 10% in the variance, so that requires 800 samples. That is totally unrealistic. So what was unrealistic was actually the goal of having a 10% of variability in the variance, and if you use more typical sample sizes with animals, it is something like 5-10. In some other contexts can go up to 30. what you see is that the delta is much higher. So the precision was 1 plus delta, so 1 plus delta here, it is almost 3. So that means that the uncertainty that you have in the variance can be, so you measure a variance, a sample variance, and the true variance can be up to 3 times more, and on the other side it is about 3 times less. So you have almost an order of magnitude for the variance. So yeah, so it is quite a lot of variation. Then so that is why I mean that you get almost the same kind of information, or even more, if you go for a previous publication and you try to measure the standard deviation there in some way, because typically they have graphs, they have some figures with error bars, and you can infer what was the standard deviation, or even they may report. So those getting the information in that way is almost the same, or even better than doing a pilot study in which you will get a lot of uncertainty. Okay, so what about the mean? So for the mean, you want again to determine the mean of this gene expression with a standard deviation of 10% of the sample standard deviation. Okay, so not with the standard deviation, with the precision, that is 10% of the sample standard deviation. So you need to start with something that you know. So this is the sample mean, this is the true mean, and this is the sample standard deviation. And you know that this ratio is distributed as a t-student with n-1 degrees of freedom. So again, you construct your confidence interval, and from there, you can construct what is the right side. So you can infer what is the sample size. So the right side determines the precision. So this is delta. So you want this to be smaller than delta, and then you have an equation for n. Again, you plug in your data, and you need almost 400 samples. So not as many as before. Before it was 800. So being 10% of precise in the mean is easier than in the variance, but still it is quite a lot of samples. So typical sample sizes in pilot studies, you have delta, that is 124, 70, 37. So that means that once you have a measurement of the sample mean, the true mean can be that one plus minus this delta times the standard deviation of the sample. So it is almost plus minus the standard deviation. It is almost 1, this number. So it is more precise than before, but still you get a lot of uncertainty. Okay, so the coefficient variation is the ratio between the two. And the problem with the sample size for the standard deviation is that you need to know more or less in which region the coefficient of variation will be, because the standard deviation of the coefficient of variation depends on your estimate of the coefficient of variation, so it is not that easy. But let's say that in this gene expression we foresee that the standard deviation will be more or less as large as the mean, so the coefficient of variation is around 1, and you have that this thing is distributed as a Gaussian, so you have the Gaussian confidence intervals, and then we have the typical sample sizes for Gaussian confidence interval. So it is the confidence term divided by the effect size, or the width of the confidence interval, normalized in a proper way. So again, we substitute and we get about 600. And if the coefficient variation was much smaller, so let's say 0.5, then it drops dramatically, so almost by a factor 10. So That means that that makes sense, because the more variable something the observations are, the wider the confidence interval. So if the coefficient of variation, that is how variable the observations are with respect to the mean, so do they change like 10% or 20% of the mean or 100% of the mean? So if they change their variability, you need many less. So if they decrease their variability, you need many less samples to have a given precision. Okay, so let's see with proportions. With proportions, it's even worse. So let's say that you want to determine the proportion of heavy smokers. Heavy smokers are those that smoke more than 5 cigarettes per day, that develop lung cancer between an age of between 40 and 50 years old, and you want to have a precision of 2% and a confidence level of 95%, and you expect the, the proportion to be around 15%. How many samples do you need for that? So if this is the central value, with this precision you want to have plus minus, loosely speaking, plus minus this 2%. Okay, so we will use the normal approximation that is valid when n times p is larger than 5 and n times 1 minus p is larger than 5, and then this statistic is distributed as a Gaussian 0, 1, and at the end, from this knowledge, you can construct your equation for the sample size based on the limits of the confidence interval. And again, it is like always, so the confidence level term divided by the width of the confidence interval and normalized in a proper way. So now you will need 1200 samples. Again, this is not a pilot study, this is a real study. So again, the problem was that we wanted to be very precise, so this 2% of variation was unrealistic from the very beginning. Okay, so what happens with the small proportions, with very small proportions? So let's say that you are working with vaccines where the number of infected animals can be very small. Okay, so or for instance adverse effects. So you want to conduct a pilot study to determine whether an uncommon adverse effect that will occur between 1% and 0.1% of the population, and you want to have this precision of 10% with a confidence level of 95. So again, you need to know how to construct the confidence intervals, and for that we will use the Poisson distribution. And the worst case is the more rare events, so it is 0.1, and the limits for this upper and lower bound will be this 0.9 lambda, 1.1 lambda, and this 0.9 and 1.1 comes from the fact that we want to a 10% of precision. Okay, and then we have to find the critical values k prime such that from that point to the left you have alpha half, and to the right you have alpha half 2. Okay, so yeah, you calculate k prime, and the n is 400,000. And again, the problem is all the time the same, that these are very rare events, so in a small sample size you will not see them, and on top of that you want to be very precise, so that is why you get such a huge number. So in general, pilot studies, the kind of, if you want to be precise, you will not conduct a pilot study, it will be a normal study. And if you run with a low number of samples, then the variability that you get and the uncertainty that you get is too high. And yeah, if instead of using the Gaussian you want to use some approximation, then you can make much more easier calculations, and it is more or less in the same ballpark number. Okay, so in conclusions, pilot studies with 5 to 10 samples result in very low statistical precision. If it is probably the same kind of precision is probably obtained from previous publications on related topics. And pilot studies are good for experimental logistic checks rather than statistical reasons. So unless what you are measuring is an alien, so if it is absolutely unknown, then you will have to pick up a few aliens, a few observations, and see how variable and what is the ballpark value of those means and standard deviations. But otherwise, you get very low information from pilot studies. And if you are interested in this topic, you may look at this article where we have tables given the precision that you want, and there is an online web calculator associated to this article, so you can calculate your sample size for your pilot study. And this would be all. So, and with this we also finish our course on sample size. So I hope you have enjoyed and learned the complexity of the sample size calculations and how they depend the specific formulas, and they depend a lot on what is your problem. So really you have to map your problem into something that can be calculated. And this is all.